is Fewster from York, and the title is Quantum Energy Inequalities. Please go ahead.
Thank you very much. Well, thank you to all the organizers for the invitation. I'm going to talk about something related to what Stefan ended with, quantum energy conditions. I'm going to talk mainly about quantum energy inequalities, which is something I've worked on for quite a long time. But it's a very old subject now, because it's over 50 years since it was known that classical energy conditions are violated in all forms of quantum field theory. And it is this year 30 years since Larry Ford proved the first quantum energy inequality that found constraints on this in quantum field theory. And so what I wanted to do is give you a bit of a sense of the current status of these quantum energy inequalities, and in particularly the rigorously derived ones. And there are two literature sources I would recommend to you. One by myself, immodestly, in Wormholes, Warp Drives and Energy Conditions, published a few years ago, a review, and there's an earlier version of that on the archive, and a recent review by Eleni Contu and Sanders on energy conditions in gravity and quantum field theory, published last year in Classical and Quantum Gravity. So I want to start in 1965, which was a very exciting year for various reasons, and I'm going to pick out only two papers from that year. One was by Roger Penrose, which got him a Nobel Prize last year, as we know. He was trying to show that the occurrence of singularities in general relativity was not an artifact of particular artificially simple models or highly symmetric situations, but was something that occurred quite generically for all forms of matter. And the only assumption that he made on matter in this theorem was the non-negativeness of local energy, or the weak energy condition, as we would now call it, that if you take a four velocity of an observer and contract it twice into the stress tensor, you get a non-negative answer. So that was his only assumption. At the same time, there was another paper written by Epstein, Glaser, and Jaffe. They wanted to show that the non-positivity of energy density in quantum field theory was not an artifact of artificially simple models like the free scalar field or free electromagnetic field, but was in fact a generic feature of all forms of quantum field theory. So we have two papers, each trying to show that one thing is not an artifact of simple models, pointing in actually quite different directions. Which is an amusing coincidence of time. The Epstein-Glaser-Jaffe paper was written slightly before Penrose's paper, but came out a couple of months after that. And in there, they already say that it was well known that the energy density in a quantum field theory can be non-positive, and their point is to extend that to all Whiteman quantum field theories. So I want to give you a sort of boiled down version of this argument. This is not quite exactly the way they put it, but it gives the basic idea. Suppose we take any Whiteman quantum field theory and we have a self-adjoint operator, which is supposed to be a smeared field with a vanishing vacuum expectation value, like so. Well, by the Ray-Schlieder theorem, we can know that there must be non-zero fluctuations. And that's because this smeared field cannot annihilate the vacuum vector, and because when you define the fluctuation squared, it's the difference of this norm squared that we've just agreed is greater than zero, and the vacuum expectation value squared, which we've also said is zero. So this has to be positive, and now you have a random variable which has zero mean and non-zero fluctuation, and it immediately follows from that that there is a non-zero probability of getting negative results. And this is true for my smeared field, even if I'm taking a non-negative test function to smear with. So if we now apply the standard interpretative framework of quantum mechanics, this tells us that our smeared field must have some negative spectrum, because measurement outcomes are spectral points. And if it has negative spectrum, then there must be other states that have negative expectation values. So in this way, one goes from very general principles to the existence of states with negative expected energy density. And one can push that a little further if we assume that this field has a non-trivial scaling limit in the sense of Fredenhagen and Haag, with a positive canonical scaling dimension. And if you make that assumption, we can prove the following. For any point in Minkowski space, let's take 4 dimensions, for example, there are states that are linear combinations of the vacuum vector and smearings of this field of interest applied to the vacuum vector with the following property. They're all normalized, the sequence tends to the vacuum vector, and the expected energy density at the point P, tends to -infinity. Okay, so this shows that the pointwise energy density of the field is unbounded below as a quadratic form on n intersection L, L being this space of states, for any neighborhood of the vacuum vector. So we have a somewhat unstable situation here. The energy conditions of classical physics are extremely unstable when quantum field theory is switched on in this sense. Any perturbation or small neighborhood around the vacuum has states of arbitrarily large negative energy density. So that is a sort of boiled down version of what Epstein, Glaser, and Jaffe were saying. I'm now going to skip ahead from 65 to 78, when Larry Ford wrote a paper on coherence effects and the second law of thermodynamics. And this is probably the only thermodynamic content to my talk, I'm afraid. So Larry took the following viewpoint. He argued that if there really were unrestricted negative energy fluxes in nature, then perhaps you would be able to create macroscopic violations of the second law of thermodynamics. But we don't see them. So this might indicate that there is some sort of restriction built into quantum field theory, which, for example, limits the magnitude and duration of any negative energy flux, so that the magnitude is less than or equal to the inverse square of the duration, and that this should be a feature holding for all states of the theory. Now, Larry wrote that he did not know of a general proof of the statement, and he also wasn't completely convinced by this thermodynamic argument, though it certainly was a good motivation. And an interesting sidelight on how things have developed is that Larry clearly felt that conclusions about thermodynamics should be derived from thermodynamics should be derived from quantum field theory rather than the other way around. And in a conference on now entropy and quantum field theory, some 40 years later, it's interesting how things change a little bit. However, this remained a conjecture for quite a while until 1991, which was the first point when Larry had a derivation of what we will call a quantum energy inequality. And for massless free fields in 4 dimensions, he showed that if you take the component of the flux and take its expectation value and average it against this sort of Lorentzian function, then the result is bounded below by 1 over Tor squared. So this is a formal version of the conjecture he'd had back in '78. Now, this wasn't a rigorous piece of work in that Larry didn't specify which states he was talking about, and there were some formal manipulations, but it wouldn't really be very hard to fix this up and make a fully rigorous statement if you wanted to. This set in train quite a lot of work, and between 1991 and 1999, Ford, Roman, Penning, Flanagan, myself, Everson, Theo, Follick, and a number of others proved similar bounds for free fields in flat and curved space-times. It was still mostly formal. There were some nice applications to wormholes and warp drive, which people had suggested might be sustained by negative energies produced in quantum field theory. And there was an interesting aspect to the phenomenology of negative energy density that goes by the name of the quantum interest phenomenon. Now, I'm not going to describe all of this. It's a long talk in its own right, but I want to move on to a tour of the mathematically rigorous quantum energy inequalities that have been proved since. And the first of these comes from 2000. It's a result of mine, and I'm going to present a version closer to one that I came up with my student Calvin Smith in 2008. And we're considering the minimally coupled quantized scalar field on any globally hyperbolic spacetime M. Okay, so this is for curved spacetimes as well as flat. We choose a coordinate chart, a nice sort of coordinate chart that I'll call a hyperbolic chart. This is one in which the 0th coordinate, as you might expect, corresponds to a future pointing time-like direction. And importantly, there is a sort of coordinate speed of light, maximum speed of light in this chart. Okay, so all causal vectors seem to obey some causal covectors obey a light cone condition like so. So in one of these charts, the following theorem can be proved. For any Hadamard state omega on the algebra of smeared fields, we take our field, our scalar field, we apply any partial differential operator with real coefficients, we take its renormalized square, and we integrate against a density. So H here is going to be a compactly supported half density supported inside our coordinate chart domain, and it's real valued. And the claim is that when we take the expectation value of that operator in state omega, it's bounded by the same operator, but its expectation value in some reference state, which is also Hadamard, minus an integral. And the integral involves various things computed in the GNS representation of this reference state. And here we see our differentiated field, and it gets applied to, here's our half density, and here is another half density, E psi, which is defined in the chart. Okay, we define it by its values in this particular chart, where it is just an exponential phase. So putting those two together, we have a density. We can plug that into our field. We get an operator. We can represent it. We can apply it to the vacuum vector, and we can take its norm squared. So that's what all of this is. And then we just have to integrate that over a half space. Okay, and here we take the half space where it's the 0th component that is positive, and everything else can do whatever it likes. So that is the bound. And the claim is that this holds for all Hadamard states. And here the choice of the reference state is arbitrary, provided it's Hadamard. So this is a lower bound. Notice that the right-hand side has no mention of our state of interest, omega, so it's state independent. The news that's not quite so good is that this is not expected to be a sharp bound, but nonetheless, it is a lower bound. I praised it in terms of restriction to a particular chart. Well, of course, we can go general by using a partition of unity. And there are versions of this argument that apply to averaging over other Lorentzian submanifolds, including arbitrary time-like curves, which is the form in which it was first proved. This right-hand side, surprisingly enough, is independent of the reference state. And you can come up with a version, this is what I did with Smith, which is based on the Hadamard parametrics rather than using a reference state. But it turns out that the answer you get is actually equal to what you get for any reference state, which is quite nice. Now, moving back towards the energy density and so on, if we had two future-directed time-like vector fields, it is a fact that the classical stress tensor of the scalar field contracted with these two vectors, vector field, can be decomposed as a sum of squares in which we have partial differential operators pi acting on our field. And because we have a sum of squares, this is obviously non-negative. And for this reason, the classical real scalar field obeys the dominant energy condition, which is precisely this inequality. But now we can take that fact and we can take this theorem and put them together and immediately deduce that there is a quantum dominant energy condition, dominant energy inequality, I should say, that if we take expectation values of the renormalized stress tensor, weighted with some density h squared with our U tensor V, and we take the infimum over all Hadamard states, there is a lower bound that is finite, independent, of course, of any of these Hadamard states, and depends on our two vector fields and the space-time and our half density H and so on. And specializing this to the case where V equals U, we get an inequality on the energy density for the quantized field, which is the quantum weak energy inequality. So that is the claim. I want to give a quick interpretation of this before I describe the proof. Suppose we take a Hadamard state that has strictly positive contraction with our fields, with our vector fields U and V when we average against H squared, right? So this is some way from the vacuum. And then if you have this quantum energy inequality, you can prove the following, that for every Hadamard vector state in the GNS domain of our state omega 0, the expectation value of the averaged dominant energy, if you like, in this state omega psi is bounded below by something a little bit less than the average in the reference state, minus some multiple of the fluctuation of this energy density in the reference state, minus something involving the quantum energy inequality lower bound that I just gave you on the previous slide, or showed that it existed. And the multiplying factor nu here is nothing other than the vector norm difference between these two states. Okay, so putting it all more shortly, and this is a very trivial calculation based on what I've told you before, but it tells you that every Hadamard state that obeys the dominant energy condition on average has a quantifiable neighborhood of Hadamard states that also obey the dominant energy condition on average. And this should be compared with what happened with the vacuum vector, where any neighborhood of the vacuum vector has states with arbitrarily negative energy density, okay, even relatively civilized one. So the existence of this state-independent quantum inequality tells you that the dominant energy condition and therefore the weak energy condition are in some sense stabilized in quantum field theory, at least away from zero. So I want to go through the proof of this because it's quite instructive. We start by subtracting the expectation values of these two renormalized squares. And this can be written in our special chart. Here is the chart expression of the half density squared. And here is the chart expression of the differentiated difference between the 2-point functions of our original state and the reference state. So it's written like this. I have x comma x here, and what I will do is split those apart by writing them as now a double integral, and here I have x and y, but then I have to pull them back together by inserting a delta function, which I do by writing it in its Fourier representation form. So overall, I get this integral expression here. I then use the fact that the canonical commutation relations of the free theory tell us that the antisymmetric parts of W and W0 are the same. So D is actually symmetric, and I can now trade my integral for a factor of 2 and an integral over a half space. Rewriting that lot in terms of the 2-point function differentiated, we can now see that we have the difference between two terms, in each of which we're plugging in this a complex conjugate of a test function into one slot and the test function itself into the other. So this is, by the positive type property of two-point functions, a difference of positive terms. And I can now throw away one of them and get an inequality, which can be written now as an expectation value of smeared fields. And rewriting that lot in the GNS representation gives us the other term that I wrote down in the bound. So using relatively straightforward properties of quantum field theory, we get to this bound. And to finish it off, I need to prove that this integral is finite. And here we use the microlocal understanding of the Hadamard condition, and in particular in this nice form due to Strohmeyer, Vollenberg, and Fech, namely that we can use any state to create a Hilbert space representation, and we can build a vector value distribution in this way. Your test function gets plugged into your field, you then represent it, you apply it to the vacuum vector, and you have a vector in the Hilbert space. And they showed that the Hadamard condition was equivalent to the wavefront set of this distribution lying in the cone of path-directed null covectors. Okay. For our purposes, the importance of that is that this norm squared decays rapidly outside a cone living in the negative half space. And this goes back to this choice of the hyperbolic coordinate chart. Of course, I have a null cone at every point in my coordinate chart. This hyperbolicity condition more or less says that all of those cones can be put inside a single cone that still lives inside the negative half space. Okay, so it allows me to bound this integral as I need to. So the integrand tends to 0 rapidly as we go to infinity. Therefore, the integral is finite, and that concludes the proof. Okay, I want to give a bit of an example. This was originally proved for averages along time-like curves, and you can make that explicit, for example, in Minkowski. And in that framework, what we find is that the average of the energy density along this curve multiplied by h squared, where h is now a test function, can be bounded below by a constant multiple of the L2 norm of the kth derivative. This is in 2k dimensional Minkowski space. And the constants are known. For example, in 4 dimensions, we have 1/16 pi squared. We get tighter bounds if the field is actually massive. Now, there's a nice consequence of this using a variational argument, which says that the supremum of the energy density over any interval of duration tau is bounded below by this quantity here. So this is rather like one of Larry's original formulations of the quantum energy inequalities, but here it comes out of the rigorous proof of an energy inequality that I told you about. So this quantity has the duration to the power of the dimension downstairs. It has this constant C2k, and the other piece here is an eigenvalue. It's the lowest eigenvalue of the kth power of minus d2 dx squared on the unit interval with generalized Dirichlet boundary conditions. So this, if you like, is a sort of uncertainty principle form of the bound. It tells you that the energy density cannot be less than this value here for a duration longer than tau. Okay, but this comes out of the quantum energy inequalities rather than being the input from which you derive it. Okay, so going a bit further, essentially this argument can be used to prove other quantum energy inequalities. It works for the free Bose fields, Maxwell-Procker, You can even go beyond ordinary Maxwell theory to premetric electrodynamics, where you have birefringence phenomena and various things like that. You can also go to the Dirac field. You have to use a slightly different argument, but in a sense, it's a cousin of the one that I've just written down. And that even has been extended in some simplified form to the Rarita-Schwinger field as well. So, on the other hand, there are no bounds of this type if we are trying to average over a space-like hypersurface. So the element of time averaging is crucial here. And there are no inequalities for averages along segments of null curves. Okay, and this can be seen by explicit constructions. And it's also somewhat related to the fact that there are no local observables associated with segments of null curves. And maybe one point in relation to ANEC and things like that. The ANEC operator is quite an interesting one because, of course, it is global. And the problem is you cannot easily approach it by integrals along finite segments of the null curve, at least not if you want them to be bounded below, because they will not be. Okay, going a little bit, taking one step beyond linear fields, I want to think about the generalized free field now. So suppose we have a generalized free field. It's going to have a discrete mass spectrum, countably infinite, with masses mj. And in this instance, we can find a bound simply by adding up the bounds that we would have for individual free scalar fields. And what results is a bound in which we have an integral rather like ones we've seen before. Here I've written it in Fourier space. And we also have a factor. The new ingredient is the counting function that counts how many species have their mass below threshold U. So this function actually ties the existence of quantum energy inequalities to the growth of our function n. And that function n and its growth are related to nuclearity criteria, due originally to Buchholz and Fishman, that essentially count the number of degrees of freedom available to the theory per unit volume in phase space. That's the interpretation of these criteria. So we can make that precise in some way. We can take any test function chi that is even and non-negative and has a non-negative transform. And then we define a new test function, a slightly strange looking combination. We convolve chi with itself and divide by t squared plus beta squared. So then there's a theorem which says that for our generalized free field, as I previously described, take the energy density along the time axis, say, integrate it against our curious test function defined up here, suitably scaled, and then take the infimum over the natural class of states to consider that I was on the previous slide. And then, if it should happen that this infimum is finite and at worst polynomially diverging as lambda, the scaling parameter, goes to 0, then one can prove a number of things about this model. Firstly, the thermal equilibrium states exist and are locally normal to the vacuum at all temperatures. And in fact, you don't need this finer detail here. You just need that the infimum is finite for all lambda. One can also prove that the nuclearity criterion holds, and as a result of that, the theory must have the split property. So in particular, the von Neumann algebra generated by those algebras for regions at space-like separation can be decomposed in a tensor product, at least provided that there's space-like separation and a safety margin. So this is a very nice way of going from quantum energy inequalities of a certain sort to the split property. And there are some results going in the other direction as well in this generalized free field model. Going one step further from linear fields, there are results due to myself and Stefan on conformal field theories in 1+1 dimensional Minkowski. And here we were able to show that any unitary positive energy conformal field theory, obeying, well, some other axioms clearly stated, has the following property, that each of the chiral components obeys a quantum energy inequality where we average this component against h squared, and we get a bound where the L2 norm of the first derivative turns up, and there's a coefficient in which the central charge of the theory appears. This bound, although it's got the same functional form as we would have had from the bound I told you about earlier in 2 dimensions, is actually sharp. This constant here is smaller than the one coming out of my earlier result. And this result here holds for all normalized states in the Whiteman domain of the theory, and so for suitable mixtures. It applies in particular to all the minimal models because we showed that the Virasoro representations satisfy all of our axioms. And at the core of the thing is the transformation property for the components of the chiral components of stress energy tensor with respect to diffeomorphisms. And they have the expected transformation rule with an anomaly that turns out to involve a Schwarzian derivative of diffeomorphism on the line. And it's this term here, you can see the coefficient actually matches up. After you've been through it all, it turns out that this term precisely gives you the lower bound in this sharp QEI. So those are it's a whole class of theories other than linear theories that obey these quantum energy inequalities. The next stop on our tour, I feel like we are going round Rome, somewhere on the Colosseum, and I'm shouting out the locations as we go by. The next stop on the tour is the massive Ising model. So this is an integrable model, also 2-dimensional. It's a theory of spin zero massive bosons. And the rigorous construction, as we know, is due to Gandalf-Lechner. It has a very nice feature, which is that the stress energy tensor of this theory is actually shared with a massive free fermion. And since we already have quantum energy inequalities for massive free fermions, we get our quantum energy inequalities for free in this model. So that sounds as though it's a little bit of a cheap trick, and you might think, well, nothing's happened very much. But I do want to emphasize that this is a truly interacting theory, albeit a very simple one. The S matrix is non-trivial. We have the 2-particle S matrix is minus the identity, not the identity. But the most striking fact is that the stress energy tensor is not additive when you tensor together single particle states. So here's a graph. Here's a plot of the energy density in a particular single particle state of this Ising model. Time's running this way, space is running that way, and you can see that there's a sort of trough of negative energy density almost in a null direction, almost pointing along the null axis. Looking just at the x equals 0 line, you'd get this plot here, the red curve. And we have a positive energy density peak and then a negative energy density trough and another peak and so on. So that's for one particle. If you tensor together this state with itself, you get a 2-particle state, and its energy density is given by the blue curve. And we see it's non-negative, at least on this part of the plot. I seem to remember that somewhere over here it might dip a little negative, but that's beside the point. Whatever it is, it's not equal to twice what you have for the single particle state. Whereas for free fields, you would expect that when you tensor together a single particle state, you will have additivity of the stress tensor because the 2 particles do not interact with one another. There's no interaction energy. So we see here that this is a genuinely interacting model but it nonetheless has a quantum energy inequality constraining its energy density. Henning Bostelmann and Daniela Cadimuro, who are my co-authors on this one, then took this further and looked at other factorizing S-matrix models. Mostly they looked at single particle states. This is in some sense because the form factor program, that's partly one of the tools that comes in here, well, it gives you very unpleasant expressions to work with very quickly. And so that has limited progress in that direction. But still, they are able to say that there are some results about the single particle sector in more interesting factorizing S-matrix models. Now, all of the inequalities that I've given you so far have had state-independent bounds, that the infimum over a class of states of some averaged energy density is finite. This is not actually going to be the case for general quantum field theories, and one can even find this behavior in linear fields. So there are interesting quantities that are not sums of squares, and so I can't apply my general argument directly. So one is that if we weren't using the minimally coupled scalar, but we added a term like this to the Lagrangian density, then the energy density would not be a sum of squares anymore. And another is that if we were to look at what's called the effective energy density, which is the ordinary energy density minus some multiple of the trace of the stress tensor, which turns up in Hawking's singularity theorem. It's related to the strong energy condition. This is also not a sum of squares. And indeed, the classical free scalar field would not, with mass, would not give you this being positive. But what you can do, at least in some cases, is do a little bit of integration by parts and discover that you get back to a sum of squares form modulo some remainder term. And then, of course, you can apply the general argument to the sum of the squares and take the remainder on the chin. And if you do that, you get a state-dependent QEI. And here is one for the non-minimally coupled scalar field from the previous slide. If we integrate the energy density times the square of some test function along a time-like curve, we get a state-independent piece to the lower bound, and then another term where the conformal coupling psi turns up, and then we have an average of the expectation of the Wick square in our state of interest. So this is the same state as was over there, weighted by some test function h that is determined by little h and the curve and the curvature of the space-time. So this was proved by myself and my former student Lutz Osterbrink. I want to point out a couple of features. Firstly, there is a sort of gain of derivatives phenomenon, like as happens in the strong Gording inequalities of pseudo-differential operator theory. The stress tensor, of course, is formed from derivatives of the field, whereas on the right-hand side, we do see the field, but not differentiated. So we've gained two derivatives altogether, going from one side to the other. And in a similar vein, while this expression here is a lower bound for the left-hand side, it is not something that can be turned into a bound for an upper bound for the left-hand side, just by multiplying by a constant. So there is a sort of one-sided aspect to this bound. We have a tighter lower bound than we could ever hope to have as an upper bound, even up to constants. And in this sense, one would say that this constitutes a non-trivial lower bound, because once we are allowing state-dependent bounds, you could almost imagine anything on this right-hand side, and you have to say what would count as a good bound rather than a bad bound. So one could do the same for the effective energy density, and there's an interesting result in the other direction due to Ko Sanders and Eleni Kontu, which says that if you actually were to have state-independent quantum energy inequalities in this sort of free field scenario, then the corresponding classical quantity has to obey a classical energy condition. Okay, that's an elegant little argument that they give in their review. So the last stop on our tour of the energy QEIs that have been derived is in general quantum field theories. It's due to Henning Bosteln and myself. It applies to AQFT with an additional microscopic phase space condition. And this was Henning's thesis work originally. And in his thesis, he showed that this phase space condition, which is a sort of variant of nuclearity, is enough to show that the fields associated with the theory, the sort of Fredenhagen-Hertel sense, can be graded into finite dimensional spaces and emit nice operator product expansions. So what we were able to show was the following result. I'm being a little sketchy here, but to every classically positive operator product, so think in your mind a square of a field or something like that, or a sum of squares, there is an inequality of the following form. We have a sum of expectation values in some state psi, and there is a sort of error term here. Now, this is actually not something to worry about too much, because I'm going to argue it's small, but it's something we couldn't get rid of. It, of course, measures the energy of the state, and it measures something about a test function, and there is another parameter here, this epsilon d. Well, what are the pieces here? Firstly, these fields phi j, they come from the OPE that is associated with this classical product. The test functions fj, those are real valued. They are derived from a basic test function that you've chosen that's supported between -d and d. They are real valued, but they're not necessarily positive. And here we have some sort of a Sobolev norm of our basic test function g, and this parameter epsilon is something that tends to 0 as d goes to 0. So this is what I mean about this term here being on the small side. At sufficiently small scales, if you don't let the energy grow too much, this is a small error. Okay, so morally, it's the inequality is that this collection of expectation values is greater than 0. Now, one way of reading that is if you can pull out one of those fields and say that that is either the dominant one or the most interesting one, and take all of the others to the right-hand side, and then you're saying that the expectation value of your dominant field is greater than or equal to, well, some collection of expectation values of other fields smeared against other test functions. And if you've chosen everything correctly, then those other subdominant fields will be in some sense of lower order. Just like we had before, we had a stress tensor on one side and a Wick square of the field on the other. That's the sort of thing that you would try to get. And in that sense, you have a general way of obtaining state-dependent quantum energy inequalities in a general quantum field theory with this microscopic phase space condition. The fly in the ointment is that we weren't able, in general, to see a good way of connecting to the energy density. And that's the weak point of this argument. But if you can say that the energy density is associated with a classically positive operator product, then there is a general quantum energy inequality. Okay, I have one topic left. How am I doing for time?
You have 6 more minutes.
Oh, 6 more minutes. Oh, plenty. So I want to now switch topics slightly to some more recent work. which is not so much about expectation values, but about probability distributions. And so supposing that you consider an averaged energy density operator of some sort, and you make an individual measurement in some specified state. Well, we know that the outcomes are distributed according to some probability distribution, and we'd like to know more about it. Everything I've said before is about the expectation value of such measurements. Well, in CFT, we can answer that to a certain extent for the vacuum state, thermal states, and highest weight states in one of two ways. One way is to solve a sort of flow equation. You start with the function that you're averaging your stress tensor against, you make that into a flow equation, and out of that, eventually, comes the moment generating function for the probability distribution. And an alternative, which is more work of myself and Stefan, is to solve a conformal welding problem. And if you go down that route, you end up eventually with the characteristic function of the probability. It's Fourier transform, in other words. So we have these two methods. Fourier transforms are definitely nicer than Laplace transforms. So this one is nicer. In many ways, it's a more elegant mathematical treatment. If you want to get closed form solutions, it turns out that the other one is so far in the lead. There are some closed form expressions for different sorts of sampling functions, and all the ones that we've been able to push through to a closed form keep coming up with a certain sort of probability distribution called a shifted gamma. Now we know that there are other distributions where we can't get closed form results, and we know that whatever it is, it's not a shifted gamma, but the ones that come out in closed form so far are shifted gammas. So here is an example. In CFT, we take a single chiral component and average it against a Gaussian, and we consider the distribution of outcomes in the vacuum state. And it's given by this probability density function here. We see that there is a cutoff. The energy density is, the probability density is 0 below some cutoff, and that's actually given by the quantum energy inequality bound. There is a long exponential tail into the positives. These parameters, beta and alpha and omega 0, are all determined by the Gaussian and the central charge. But what I want to point out is a very striking fact, is that if you ask, excuse me, what is the probability, what is the probability of getting a negative result? Measuring this energy density in the vacuum, it turns out to be 89%. So it is overwhelmingly likely, if you were to play this game, that you get a negative answer. And of course, it's a negative answer, but it will be a very small negative answer because the quantum energy inequality bound is usually very small. And this has to be balanced against the smaller probability of getting a very large positive result. And that's putting the two together, how the expectation value in the vacuum can come out to be 0. So this is something that can be done in closed form, and we're working on other sorts of approaches to this, numerical approaches and so on, trying to get some more information about the CFT. It's harder to get anything out of the welding method. There is one class of where there's a closed form solution, but the test function that you use is not a non-negative one. It's of indefinite sign. And amusingly enough, the distribution that comes out is a generalized hyperbolic secant that reminded me very much of the sorts of things that turned up in Stefan's talk at one point. That's probably just coincidence, but who knows? Moving to 1.1 plus 3 dimensions, there is now some heuristic calculation, or partly heuristic, and some numerical work. And what we found is that the distribution depends quite heavily on the Fourier asymptotics of the averaging function. So if I take the Wick's square of the time derivative of the field, and average it against a function of time times a function of radius, and I have this sort of asymptotics for my for the Fourier transforms is e to the minus omega to the alpha here and omega to the lambda there, then our prediction is that the tail of the probability density function looks like this. I think the main thing to focus on is these exponential factors. And there again, we see this alpha and this lambda that came from the two Fourier transforms over here. So we were fairly confident about what's up in the exponent, and distinctly not so confident about this exactly what this power should be in the front. This is what happens at very high values of the energy density. At lower regions, we also predicted that there should be a different sort of shape to the PDF, and notice that the power here has changed. So this should be an altogether slower tail, a heavier tail at that point, that then at some point turns around and becomes quicker. So those were our predictions, and some numerics from this year from Wu and Ford and Schiappa-Casa show very good agreement with those predictions. Here is a log-log plot of the probability density, and because it's straight line, that tells you that indeed we have this e to the minus power. The gradient of this curve is in really rather excellent agreement with what we said, to maybe a couple of decimal places. And down here, you see that there's a different straight line, more or less. It's sort of bent round, becoming straight down there. The agreement with our other gradient is sort of more moderate, but it's certainly the right ballpark. So we see these effects, and this gives us some more confidence in our heuristics. So I think with that, I come to the conclusion. I've given you a tour of the QEIs for free models. They're mathematically rigorous in flat and curved space-time. I've shown you the tour of other theories where they hold, CFTs, Ising model, and some general theories, though less with some caveat, and that there is information about the probability distribution of individual measurements. It's clear that the ingredients for a truly general QEI, which really does connect to energy density, must involve some form of nuclearity, must involve some sort of state dependence, and must have some accompanying idea of non-triviality. Otherwise, it could just be vacuous. So with that, I will conclude. There is a whole bunch of things that I would like to have talked about, but there's simply not enough time for everything. So with that, I thank you.
Thank you a lot, Chris. Very nice talk. Now, is there any question? Maybe I ask a question concerning the construction KMS state. If I understand, you have a better, in a sense, a better condition than Buchholz and Junglast, and you can construct locally normal states, no? Locally normal KMS states. Are these states unique, or do you have conditions for uniqueness?
No, we did not. We took, in fact, I would not say we've done better than Buchholz and Junglast, because we are really using their results. What we do is we prove that the nuclearity criterion that they used applies, and therefore we have essentially tagged into their result at that point. But it comes from, but we push it back a stage, or I should say I push it back a stage, to the existence of a quantum energy inequality. So it's more the starting point rather than the actual method of proof. As to uniqueness, that is a very interesting question. I haven't analyzed that under this setting. That would be very interesting, actually. See if it can say anything about that.
Thank you. Any further question?
I have a question.
Go ahead.
Hi, Chris.
Hi, Sebastian.
So now, if you can go back to the slide where you have this estimates with the, please, with the, as you said, product of fields. So you have this sort of OPE.
Yeah.
Yes, you got it.
Yeah. Here, this one?
Yes, this one.
Yeah.
So if I, as far as I understand, so what is the, so why, in a sense, G is the test function that you have in the product, and then you get the function Fj in the OPE, is correct?
Yes, that is correct. Yes, you get these.
Yes. So this
various...
is symmetric. So the fact that you take greater than equal or 2 or, okay, this is something on the absolute value, in fact, no, because it's symmetric in, so you should get the same with minus G, correct?
Yes, it is, because it's based essentially on G squared.
So
yes.
if you take minus G, you take minus Fj. So, and then if you have the estimate in the other direction. So
no, because it's like these other bounds. You're really thinking about
no, because
integrating in
it's
G
square.
squared. Yeah.
You have a square. Yeah.
So yes, you can switch G and minus G, but it doesn't change anything.
Okay, so you have only this. So you don't have estimate in the other. You start from a square. The point is something positive in a sense.
Yes, exactly. Okay. So all of this, it's like the extent to which quantum theory takes you across a sharp classical boundary. Okay. So squares are positive in the classical world, but they can creep a little negative in the quantum world. It's always this one-sided. Yeah.
Okay. And this you get for square or also for even powers in general? It's the same.
We didn't look at it beyond that. In principle, one can, but I think there's a similar. I mean, in a sense, you could try to think of your 2nth power as the square of 2nth powers.
Yes, okay.
That's basically how you
iterate.
Yes, exactly.
Probably. Okay.
Yes.
Thank you. Okay, this was just so.
This
is published recently because I.
This one? This is actually 2008 or thereabouts.
Oh yes, I lost this. Probably, or maybe I forgot this. But okay,
yeah.
I understand the point.
Yeah.
Thank you very much.
Okay.
Rainer?
So, hello, Chris.
Hi, Rainer.
Yeah, interesting talk. I'm coming back to the same formula here on this slide that we have. So there seems to be a relation to H bounds. So in which sense is that better or related to H bounds of quantum field operators?
Well, it is somewhat related to that, except again, the difference is yet again the semi-bounded aspect. Okay, so this is if you like, you could think of it as a lower H bound, but it is not. You are using a power that could not be used as an upper H bound. That's part of the non-triviality.
So that's part of the result.
Yes.
So
exactly.
that the L here is not sufficient for an upper bound.
Yes, we actually investigated this because this is, as I emphasize, an important aspect of these state-independent lower bounds to show that they cannot function also as upper bounds. So indeed, this power of L is not enough to give you an H bound from above.
Okay, thank you.
So, in a sense, just a comment. What is in? So I put the camera again. So what is interesting is this point that this epsilon d is going to 0.
Yes.
Because if you start from energy bounded fields, then you always get such kind of bound.
Well, yet again,
you get on both sides.
On both sides, yes.
The point are the constants.
Yes, and that you can do better on the lower end than you can on the upper end. That's it.
That's the point.
Yeah.
Okay, thank you.
Any more questions? Maybe I will ask about the inequality in the conformal field case.
Sure.
It's equivalent or related to the what Mihaly Weiner got long ago on.
If I'm not, well, there is a relation, but I think that unless there's something that I'm missing, I think our results were earlier than his. They were very much at the same time, but I think ours were slightly earlier. But there is a relation between his work. I must admit, I don't remember too well, but I think that we were, this came out ahead of what he did. But unless I've missed something.
Okay.
Yes. No, I think Mitsubishi got essentially this idea, but at the time he did not wrote really the details. So,
Okay.
So the idea was there, but there is a point that you have to pass from the strictly positive function to the non-negative functions, and there you need some details, and Chris and Stefan did carefully on the paper. And I don't know really if she has done, but was not written in case. Then he was looking for this in order to get something more, and this is what we wrote only recently, but this is another story, this local energy bounds.
Yeah.
Yes, it's related, but we use this kind of quantum energy inequality as a first step.
So, anybody want to ask a question? If not, we now offer a virtual cup of tea, and we meet again at 4:30. Enjoy. Thank you again, Chris.